In this video, we'll talk about the z-test when we have more than one person in our sample. Hopefully you've already watched the video about the z-test when we have one person in the sample, and hopefully you've already understand the basics of hypothesis testing and our 5-step hypothesis testing procedure. And now we're going to kind of extend what we've already learned by talking about the z-test when we have more than one person in our sample. The important thing that we always want to make sure to do when we first learn a new test is to make sure that we know when do we use this particular test. Because this is a z-test, we're still going to use this z-test when we know our population mean and our variance or standard deviation of our population. And so that's just going to be true for our z-tests in general. But we know that because this is the z-test with more than one person in our sample, we're going to use this when we have more than one person in our sample, just as it sounds. And so that's what's going to distinguish it. This is the new part compared to the z-test that we've talked about before. If these two things are not true, if we don't know our population mean and variance or standard deviation, or if we don't have more than one person in our sample, then this is not the correct test for us. But as long as these two things are true, we're going to move forward with our z-test with more than one person. We're going to use, again, our same 5 steps for our hypothesis testing process. We're going to make sure, though, that we are adjusting this process ever so slightly to make sure that we're using the correct procedure for this test. And so for each test that we go through, we're still going to use these 5 steps. But we've talked about the idea that how each step gets completed might change a bit depending on the test that we're using. In this particular test, we're going to see that steps 2 and steps 4 are going to differ from the z-test that we've talked about previously. So in general, we're going to restate our question as a research hypothesis and null hypothesis about populations, just as we normally would. Step 1 stays exactly the same from our original hypothesis test. And we're going to see that while the wording of that research hypothesis and null hypothesis might change slightly from test to test, step 1 generally happens the same way all of the time. Step 2, determining the characteristics of our comparison distribution, that's going to change. And that's going to change really with just about every test that we do, because our comparison distribution is going to change with every test. Specifically, our research design and our sample is going to be different, and that's what's going to make our comparison distribution different for each test. For the z-test with more than one person in our sample, we're going to call our comparison distribution the distribution of means. This is different than the comparison distribution for our other z-test, which is just the population. We're going to see, though, that this distribution of means is going to be based on the population, but it's going to be a little bit different to reflect the fact that we're using more than one person in our sample now. So when we think about the distribution of means, what we're basically doing is we're basically taking our population, and we know that in our study here, we have our population and we're taking out a sample of a certain number of people, and those are the people that we're studying. We're going to give them our medicine or teach them our study strategy or whatever that we're doing. We're going to measure their scores, and we're going to get a mean of their group scores. In our comparison distribution, what we're going to do is it's basically as though, or theoretically, we can create our distribution of means by taking a sample out of our population. So for instance, these 6 people, we take these 6 people, we get the average of their scores. In this case, our sample is 6 people, so we're going to take a group the same size as our sample. We're going to get their mean, and then we're going to start building a histogram using these means. We're going to take then another 6 people, get their mean, put that on our graph. Get another 6 people, and so on and so on. So we are going to take groups the same size as our sample, take their mean, and we're going to build a distribution based on their means. This is what's going to give us our distribution of means. And the important part here is that our distribution of means looks like our comparison distribution, rather, looks like our sample. For our original z-test, when we have one person in our sample, we use the normal distribution, we use a population, we use the distribution of individuals because we have an individual score. So we're comparing an individual to a distribution of individuals. When we're talking about our distribution of means, we want to look at our sample and say, now we have a mean, we have to compare to a distribution of means. We always have to make sure that with our comparison distributions, we're comparing apples to apples, not apples to oranges. And so that's exactly what we're doing. We have an individual, we're going to compare to a distribution of individuals. Now we have a mean, we're going to compare to a distribution of means. Exactly how it sounds. So for an example here, as we look at our hypothesis testing with more than one person in our sample, let's say that we have a hypothesis that a certain therapy is going to increase memory in dementia patients. For step one, we know that we're going to state the null hypothesis and our alternative or our research hypothesis in terms of those populations. So for instance, people with dementia who receive our therapy will remember more than people with dementia who don't receive our therapy, or people with dementia in general. And people with dementia who receive our therapy will remember the same amount as people who with dementia in general, or who will not remember more than people with dementia in general. And so when we're predicting that these people will remember more than people with dementia in general once they've received our therapy, that's going to be our research hypothesis. Predicting that these people will not remember more is going to be our null hypothesis because we're predicting no effect. We want to stop here for a moment and decide, is our hypothesis directional or non-directional? And because that we're predicting that people will remember more, we have that keyword more there, and we're going to say that this is a directional hypothesis. Now we move on to determining the characteristics of our comparison distribution, step 2 of our hypothesis testing procedure. And here we know that our comparison distribution is going to be the distribution of means. Because we have the distribution of means here, step 2 is going to change. Our comparison distribution is different, so how we determine those characteristics will be different. But we're going to see that we can get this information from our population information. And we know that because this is a z-test, we already have our population mean and our population standard deviation here. So first of all, for our mean, our distribution of means, mean, is going to be the same as our population mean. And we see that we have this new symbol here. So we have our population mean, we have that mu, that's our population mean. When we see mu with a subscript capital M, that's going to be the mean of our distribution of means. And again, this is going to be equal to our population mean. For our variance, we're going to take the variance of our population of individuals. So we have the sigma squared here that we're familiar with, and we're going to divide that by the number of individuals in our sample. And we're going to see that we're going to still use that variance symbol, sigma squared, but with that subscript capital M, just like we see here. That subscript is always going to signify that we're talking about our distribution of means. To get our standard deviation, we have the same thing. We know that standard deviation is always going to be our variance squared. And so we're just going to take that sigma squared variance divided by n, the number of people in our sample, and we're going to get the square root of that. And lastly, for the shape of our distribution, the shape of our distribution is going to be normal. It's going to be a normal distribution in two cases, and two cases only. If the distribution of the population of individuals is normal, so if our population is normal, our distribution of means will also be normal. Or if each sample is of 30 plus individuals. So even if our population is not normal, then as long as we have more than 30 people in our sample, then our distribution of means is going to be normally distributed. So let's put this into practice here. So for instance, let's say that we find out here that our population mean is 5, our population standard deviation is 2, and our population is normally distributed. And in this case, we have 6 individuals in our sample. So let's try this out here. Our distribution of means here, our mean of our distribution of means, is going to be equal to the population mean. And so we know that that is 5, our population mean is 5, the mean of our distribution of means is also going to be 5. Now for variance, we know that we can plug in our standard deviation. We want to always plug in those numbers, substitute things that are exactly the same. So we know that that's sigma squared is our variance. We have sigma here, we have our standard deviation, so we're just going to plug that in. So the variance of our distribution of means is going to be 2 squared over 6, or 4, which once we do that, once we use that exponent, we're going to do 2, so we're going to have 4 over 6 rather. And once we do that division, we're going to get 0.67. To get our variance, we can take this answer, 0.67, and go ahead and get our standard deviation. Or we can plug in those numbers and do that problem out again. Here we see our 0.67 with our square root, and we get 0.82. And we know that our population distribution is normally shaped, and so our shape for our distribution of means will also be normal. Now we have step 3. And so for step 3, this is going to be exactly the same. Because we are still using a z-test, we're still going to be using our z-table in order to determine our cutoff score. And so we have our z-score here for our cutoff score. And so for our cutoff score here, we know that we have a one-tailed test, so we don't have to do anything extra, and in this case we'll use our 5% significance level. So we'll be looking up that percentile of 0.05, or 5% in this case, and in this case we know at this point, maybe we've memorized that is going to be 1.64. So we have our significance level, we have our cutoff score rather. So next we're going to determine our sample score on the comparison distribution. And so for this step, we're going to have a new formula. Because we have a new comparison distribution, we have a new formula here. Although we're going to see that it's really very similar to the last one because it's built off of the same z-score formula that the other the hypothesis testing formula is built off of. And so here is the formula that we're going to be using. And so we can see that the symbols have changed a little bit. So we have a mean now instead of one raw score. We have the comparison distribution changing here with these subscripts of m for this distribution of means instead of just the population. And we have to, again, consider what we know here. We have, in step 2, we have that information of what's the standard deviation of our distribution of means, what's the mean of our distribution of means, and we have this information now. And the new information now is we might have our 6 scores that we need to get the mean of, or we might just have the mean already calculated for us for that sample. And so we get this information that our mean for our sample, and note the symbol there for our sample mean, is 6.64. And so what we're going to do is we're going to just plug in our numbers. N, again, is 6.64 minus the mean of our comparison distribution, the mean of our distribution of means, which is 5, so 6.64 minus 5, and then divide that answer by 0.82. So we get 1.64 divided by 0.82, which is going to equal 2. And lastly, step 5 is going to be just the same. Really, step 5 is going to be one of those steps that's going to be the same no matter almost whatever type of hypothesis test that we're using. And so how do we decide whether we reject or fail to reject our null hypothesis? And so again, I encourage you to draw this out. It's particularly very helpful to be able to visualize this, be able to see it. And so we said that our cutoff score is going to be 1.64. So we've graphed that here. Our sample z-score we said was 2. And so we can see that our sample z-score is going to be further out in the tails. It's more extreme than our cutoff score, and we're going to be able to reject our null hypothesis here.